AlphaGo and AlphaGo Zero are the two Go-playing agents developed by Google subsidiary DeepMind. This system combined deep convolutional neural networks with self-play reinforcement learning to achieve a tremendous leap forward over previous Go algorithms, and in 2016 became the first Go AI to defeat a human world champion. In this video, I'll explain how DeepMind created these systems and cover some of the highlights from the research papers they published about both AlphaGo and AlphaGo Zero. Go is a two-player game that occupies a similar position in East Asian culture to that of chess in American or European culture. The rules are incredibly simple to describe. Players alternate placing black and white stones on any empty intersection of the board, and if a stone or group of stones is completely surrounded by the opponent's pieces, it is captured and removed from the board. The game ends when both players pass, and a player's score is the number of stones they have on the board, plus the number of empty intersections their pieces surround. There's also a rule that if stones have been captured, you can't play a move that would cause a previous board position to be repeated, but that's it. And even though the rules of the game can be described in about 30 seconds, it has enormous strategic complexity. So much so that, as recently as 2015, many experts thought that Go-playing AIs that could compete with top human players were still decades away. And so it's worth asking, why did experts in both artificial intelligence and Go think that just before AlphaGo debuted in 2016? In order to plan a good move in a game like Go or chess, you have to think several steps ahead. If I play this move, then how will my opponent respond, and how will I respond to their response, and so on. The chess engine Deep Blue, which in the mid-1990s became the first to defeat a human world champion, did this by considering every possible sequence of moves and counter-moves some number of steps ahead, and then evaluating for each of the resulting board states how good is it to end up in that position. In chess, this can be done largely on the basis of which pieces have been captured and other easy-to-compute heuristics. But unfortunately in Go, evaluating the quality of a board position is a much harder problem. And in addition, Go has a much higher branching factor than chess, meaning that at any given state there are a lot more legal moves, and so to consider them all exhaustively, more than a couple of steps ahead, quickly becomes infeasible. So if we want to develop an algorithm that reasons several steps ahead in Go, we need some way of restricting the hundreds of possible moves to only the most promising few choices that we want to pay attention to. And we also need some way of determining, for the states that result from those move sequences, how good is that board position. The key innovation of AlphaGo was to solve both of these problems using deep learning. AlphaGo trained deep neural networks to solve two separate but closely related problems. Both the value network and the policy network take as input a representation of a state of the board, but the value network estimates the probability of each player winning if the game continues from that state, while the job of the policy network is to estimate the quality of each of that state's legal moves. The output of both of these models can then be incorporated into the planning algorithm, where the policy network helps restrict our attention by showing which moves are the most promising for the search to focus on, while the value network can tell us when we reach some future board state, how good would it be to end up in that position. So, to understand how the deep learning components of these systems work, let's dive into the architecture that was used and the kinds of data that they were trained on. The network architecture is one of the areas where AlphaGo and AlphaGo Zero differ substantially. In the first paper, the authors describe a plain convolutional architecture, and they talk about training separate policy and value networks. In fact, they train 3 neural networks because there are 2 different versions of the policy network, one that is optimized for accuracy and another optimized for speed. But in the newer paper, they found more success using a residual architecture and training a single core network with separate heads for the policy and value outputs. The idea of this core and head architecture is that the residual blocks can learn to detect important information about the board state that is needed for both estimating the value and picking good moves. And then each of the heads can be a much smaller network that takes all of that information about the board state that was computed by the residual blocks and outputs either a win probability or a weighting over possible moves. Within each of the blocks is a relatively standard residual architecture consisting of convolutional neurons with rectifier linear activations, along with batch normalization and a residual connection. The other big difference between AlphaGo and AlphaGo Zero is the data that they trained on. AlphaGo started its training with a large data set of games played online between high-level amateurs, whereas AlphaGo Zero used zero human knowledge in its training data. Training the value network, or the value head of the combined network, is relatively simple. The input is a board state represented by 1s for black pieces, -1s for white pieces, and 0s for empty intersections, while the targets are +1 or -1 for who ended up winning the game. And this sort of data can easily come from the human games, where we sample some board state and then look at who ended up winning the game, or they can come from games that the AI played against itself in the same way. The training data for the policy network, or the policy head of the combined network, is more complicated. If we are training with data from human games, then the sort of observations we have are, from a given board state, what move did the human play? And so the policy networks for the original AlphaGo were trained by categorical cross-entropy to just predict the human move. And when the original AlphaGo went beyond the human data by adding self-play training data, it also used just the move that was played as the training target. But the loss function also incorporated information about which agent ended up winning the game, so that it could upweight moves that led to a win and downweight moves that led to a loss. But the original AlphaGo paper actually reports that they didn't achieve a lot of improvement in the policy network from this sort of self-play training. And in fact, as of the publication date of that paper, the best version of AlphaGo used a policy network that was entirely based on learning to imitate human moves, but with a value network that had been updated using data from self-play. But for AlphaGo Zero, the authors realized that there's actually much more information available from the self-play data that can be used for training the policy network. In particular, when the planning algorithm is thinking several steps ahead and considering lots of different options for what move to play, it gathers information not just about the move it ended up playing, but in fact about all of the possible moves. So AlphaGo Zero trains the policy network on targets that are not just based on what move got played, but instead on the estimates of move quality that were produced by the search that the planning algorithm performed. Which means that, since the planning algorithm is looking several steps ahead, over time the policy network will be trained to output estimates of move quality that correspond to thinking many steps into the future. So the overall loss function that the AlphaGo Zero combined network gets trained on is a sum of a cross-entropy term for the policy head, a squared error term for the value head, and an L2 regularization term to make sure the weights don't explode. Of note, both the AlphaGo and AlphaGo Zero papers build on lots of prior work in deep reinforcement learning, where overfitting to particular aspects of a task is common. And so AlphaGo makes sure to not train on every single board state from a single game, and instead samples random board states from a large collection of games. And this ensures that the network doesn't overfit to the path of play from one particular game. And as the agent improves over time with better and better versions of the neural networks, it still hangs on to data from previous versions of the agent to make sure that it isn't overfitting to just playing against itself. So these models need to be incorporated into a planning algorithm that can take advantage of the policy network to restrict which moves are being considered, and the value network to estimate the win probability from different board states. And the planning algorithm used by both AlphaGo and AlphaGo Zero is called Monte Carlo tree search. MCTS had previously been used by other Go AIs, but without policy and value networks, was only able to compete with mid-level amateurs. With or without the deep learning components, MCTS works by performing some number of rollouts. Each MCTS rollout considers some sequence of moves beginning from the current board state. And over time, MCTS builds up a data structure to store the information it has gathered about the value of different move sequences. This figure from the AlphaGo Zero paper only shows 2 moves, but obviously in a real Go game, there could be hundreds of legal moves from a given state. But for each of those moves, MCTS stores an estimate of the move's quality and an estimate of the uncertainty about that move. The quality score is initialized based on the outputs of the policy network, which tells us for each of the legal moves how good does the model think it will be. Then over time, as the algorithm performs rollouts where it simulates playing that move, it will update the quality based on the value estimates for future states in those rollouts. The uncertainty term is based on how many times a particular move has been tried in previous rollouts. So the uncertainty term will start out equal for all of the moves, and each time the search considers a particular move, the uncertainty for that move will decrease. And so when considering which move to try in a given rollout, MCTS will pick the move that has the highest sum of the quality and uncertainty terms. This means that initially, when all of the uncertainties are equal, the highest quality move, according to the policy network's estimate, will be selected. But after we have tried that move, we will update its quality estimate based on what we found, and we will lower its uncertainty every time we try it. Which means that after we have tried a move a few times and decreased its uncertainty, other moves may end up with a higher quality plus uncertainty and get explored on future rollouts. The search continues in this way until it reaches a state that has never been seen before. While we're looking at states that have already been explored, we can pick the move with the highest quality plus uncertainty. But when we get to a new state, we have to evaluate it using our neural networks. So we can give that new state that we just found to our double-headed policy and value network, from which we'll get a value estimate, meaning the probability that we win if we reach that state, and also a quality for each of the legal moves from that state. We'll use the output of the policy network to initialize the quality scores for all of that state's legal moves, and then we will use the output of the value network to update the quality score for each of the moves that we played in the rollout that got us to this state. Which means that over time, these quality scores will become an average over the values that we found in all of the rollouts where we played that move. After a large number of these rollouts have been performed, we should have good quality estimates based on thinking several moves ahead for all of the legal moves at the current state. In addition, we should have very low uncertainty for the better moves that have been explored more times. And so to actually play a move in the game, the agent can pick among the legal moves at the current state, either the one with the highest quality or the one with the lowest uncertainty, because in general those should be the same. And then, after the move is played, the current state of the board will change, and the agent whose turn it is now can start running Monte Carlo tree search to make a plan for what move it will choose from that state. So both AlphaGo and AlphaGo Zero perform their self-play reinforcement learning by having two Monte Carlo tree search agents play against one another, and gathering data from those games to expand the training set for both the policy and value networks. And in fact, the system can be, in parallel, running self-play games between agents with the current versions of the network, and training new versions of the networks using data from the previous rounds of self-play games. During self-play, we need to store the sort of data that the networks would be trained on. So for AlphaGo Zero, that means we need to save the state of the board, which player ended up winning the game, and the quality estimates for all of the legal moves that Monte Carlo tree search found when it was evaluating that board state. Then the neural network training will use samples from these self-play games, where it will pick out a random board state to use as input, and train the value head to estimate who will win from that state, and the policy head to output quality scores that are more like the several-step look-ahead produced by Monte Carlo tree search. And over many, many iterations of playing games with the current networks and training new networks with the data from those games, we will gradually improve the quality of estimates from both the value and policy heads of the network, meaning that the agent will get better and better at playing Go. And the AlphaGo Zero paper showed that this can start completely from scratch, where the agent initially makes completely random moves. But over time, the value head will start to be able to estimate who's going to win from a given position. And then once the value head has some useful information about the quality of different states, the Monte Carlo tree search will be able to incorporate that information and make better predictions for the quality of different moves. And since the policy head is being trained to imitate those MCTS evaluations, it will eventually also learn to usefully restrict the space of possible options and make Monte Carlo tree search better and better over time. And over tens of millions of self-play games and millions of stochastic gradient descent mini-batch updates, AlphaGo Zero eventually outperformed the original AlphaGo, meaning that the version that trained itself entirely from scratch eventually outperformed the version with a huge head start from imitating humans. AlphaGo and AlphaGo Zero have achieved some very impressive results. In 2016, the original version reported in the AlphaGo paper defeated one of the best players in the world in a 5-game match. And then after a bunch of additional training, that same AlphaGo system won a sequence of 60 consecutive online matches against professional Go players, and then in additional show matches defeated both the #1 ranked player in the world and a team of top professionals collaborating against it. But in the AlphaGo Zero paper, DeepMind showed results of the new system playing against both of those older iterations of AlphaGo, and AlphaGo Zero beat them both by wide margins. Since the publication of these papers, AlphaGo, and especially AlphaGo Zero, have had a big impact on the Go community. Lots of other projects, including open source and commercial software, have replicated AlphaGo Zero's results. And while the training still takes an awful lot of self-play data, the inference phase, actually using the agent to play a game of Go, can now run on just about any computer. Which means that in online Go, cheating with bots has become a very big concern. But at the same time, this wide availability has made a big difference in how Go players study the game, where instead of using the AI to cheat, they can use the AI after the fact to analyze how well they played a game and figure out what sorts of moves they should be considering in the future to do better. Outside of the Go community, AlphaGo has also had a big impact through follow-up papers on related systems. In 2017, DeepMind also published about AlphaZero, a system that uses the AlphaGo Zero system, but swaps in the rules of a different game instead of the rules of Go. And they showed that AlphaZero can achieve very impressive performance in games like chess and shogi. And very recently, DeepMind published a new application of AlphaGo called AlphaTensor, where instead of playing a game, they're using Monte Carlo tree search and deep learning to plan the execution of matrix multiplication algorithms, and they showed that this system can devise new algorithms that improve both the big O running time and the practical efficiency on real hardware of matrix multiplication, which has the potential to someday improve all of the calculations that we do in training all the neural networks we use in deep learning.